Hello, my name is Mahdi. I am co-author of the manuscript. In this video, I'm going to share with you the implementation of fault-tolerant field-oriented control on a three-phase induction motor based on unified feed-forward method. This is the GUI for the fault-tolerant FOC by DSpace Control Desk. The drive status bar is located at top of the screen, and the real-time measurements are captured by the main plotter. Instantaneous torque is shown here, and the motor speed is over here. Control panel comes at bottom right corner. The live view of the drive is on top right. Main components of the test rig are 3-leg IGBT inverter, 6-channel current sensor, of which 3 are used, fault emulator relays, induction motor, PM motor, and the torque transducer in between. To run the drive, need to set the reference speed first and click Run. This is a balanced, healthy operation. The first test is to manually disconnect phase A of the motor. And this is how the drive tends to be, without any reconfiguration. The torque profile oscillates together with the speed. Let's return it back to healthy mode. In second approach, the fault is created by using fault emulator box. By checking this checkbox, fault emulator relay will be energized, and motor terminal A will be disconnected from inverter leg A. 100 milliseconds later, reconfiguration relay will automatically reconnect the inverter leg A to the motor neutral point, and the V0 will be switched over to be the modulating index for this leg, that is called neutral leg after this. Let's create the fault. We can pause the real-time measurement to see details of drive behavior while the drive keeps running. Following the waveforms and status bar, here the time cursor indicates the healthy operating region with dead time compensation. By moving forward, this is the instant where the fault is emulated. Simultaneously, the fault indicator turns on. The faulted drive continues with open phase fault until eventually at this point, the topology is reconfigured and the V0 is applied as the modulating index of the neutral leg. We can see the torque oscillation as well as speed oscillation are reduced, but the fault is not tolerated fully yet. After this point, the fault is almost fully tolerated and the speed is recovered nicely, since dead time and forward voltage compensations are started. So, the feed-forward fault-tolerant controller has done its role with acceptable results. The modulating index in post-fault mode looks like a broken sine wave because compensation terms of dead time and forward voltage are square wave signals. For the NCM post-fault configuration, two capacitors are connected across the DC bus to provide DC link midpoint. Let's assign the reference speed to be 1400 and run the drive. Now, the fault can be created by emulator. Can see the fault is well tolerated here too. Zoom in to have a closer look into the results. Similar to the previous configuration, before the fault happened, the motor is in healthy operating region with activated dead time compensation. The fault is obviously created over here, and the fault indicator turns on. The output torque and speed starts to oscillate as expected. By moving along, the oscillation is evident from speedometer. Afterward, the topology is reconfigured accordingly by clamping motor neutral to capacitor midpoint. Simultaneously, the V0 is deducted from the modulating index of the other two active inverter legs. The torque and speed oscillations are still there. Going forward, here is the activation instant of dead time compensation and forward voltage compensation. So, the torque profile and speed of the drive are sufficiently suppressed in post-fault mode. You can see there is no speed oscillation, means the fault is significantly tolerated. The last part is to show the self-start capability in post-fault mode. Let's run the motor in healthy mode first. The waveforms of self-start in healthy mode looks fine, as expected. So it's time to emulate the fault. And it is well tolerated. Let's stop it and restart the drive in post-fault mode. You can see the faulted drive is able to self-start successfully. The transient response contains large starting current. However, the torque and speed dynamics during self-start are acceptable.